company called Trustonic, who is one provider of trusted operating systems. But I will try to, during this half hour, give a kind of brief introduction of what the trusted execution environment is, what it means on Android devices, and then go through a few research use cases. And I try to finish in 25 minutes and leave time for questions. But if you have an urgent question, just please ask them while I'm speaking, because we don't have so much time, and we can always skip some use case if we have some interesting questions about the TE and the hardware itself. So let's start with some kind of definition of what the trusted execution environment is. So we have heard some kind of angles of it earlier during this yesterday and today's talks, but mostly it's an isolation environment where you can run some security critical things that are important to you as a stakeholder in the system, whether you are the operator or an OEM manufacturer or a third party. And so it's isolated from the normal world, but of course also isolation exists between applications. So also when we are isolated from the normal world, there will be many trusted services, and of course those trusted services shouldn't interact with each other. They should be kind of isolated in terms of their, for example, crypto keys that they get access to. Another important part of the kind of concept is the integrity of the operating system itself. So of course this also applies for the so-called normal world or big world, but if we look at the kind of the trusted execution environment, which essentially exists in parallel with the normal world, we somehow have to trust that the environment doesn't change over time, or if it changes, it at least changes in kind of an organized manner. So integrity is a very important part of it, and typically they hang off secure boot. So when we yesterday heard about verified boot, that does apply when we kind of start booting the device from the operating system upwards, but at the very bottom level, like we have bootloader 1 and 2, then there you have actually a secure boot, so you can't really change things without kind of trashing the device. So the trusted operating system hangs off that chain of trust. Then we also have integrity. We need sometimes to communicate with the user with a trusted UI. That needs integrity for the so-called trusted path. Trusted path is also used for DRM, so if you want to play something from the secure side, you need a trusted path from the secure side to the screen of the user. Rollback protection is another kind of form of integrity that's needed. If you store something, you encrypt something, you want to get it back the next time, and the latest version, not the version before that, then you need some kind of rollback protection for the secure storage. And we need secrets, confidentiality, and typically it's arranged so that the trusted execution environment gets some set of keys that are not available to anybody else in the system. And using those keys, you can diversify the keys for secure storage, some remote attestation, for example, device authentication, things like that. One part of the TE that sometimes is not kind of thought about so much, and some TE vendors don't really think this as a feature, but it's also a matter of whether you can actually get your application running in the secure side. You can envision a TE that has only kind of fixed services, like for example in the Android case, you have the key management and you have typically DRM, you may have some SIM lock for the device, and you can say that those are the only services that are needed, and then you just kind of hardwire them into the TE, and you don't allow a third party to provision a new application after the device is on the market. On the other hand, then it a little bit restricts the usability of these things. So I think we should say that also the third party provisioning is a part of a fully functional TE. And then if you look at all of these requirements, a smart card would perfectly well fill all of them. Actually, in some cases, even better than a TE. But there are some properties that also set the TE apart from a smart card. Well, one is because it's running actually in the same processor, the same core environment as the rest of the operating system. The TE runs at full memory, full speed of the processor. It also has typically direct memory access to the whole system. That means that you can actually do computing intensive services inside the TE. And also, more often than not, the code you write for that is really like a standard C application. You can envision having a Java card, a Java environment in the trusted environment, and there has been such attempts. For example, somewhere around 1995, ARM did sell a TE with a Java on the right side, on the secure side. But the problem with the interpreter is often that the interpreters tend to be quite big. And then because the memory you reserve from this is something that is taken away from the memory available to the normal Linux, to the normal Android, then you don't want to consume so much memory for the trusted part. So you are typically limited to something like 100, 200, 300 kilobytes of memory. And in those kind of restricted environments, a Java virtual machine doesn't fit at least nicely. So if we go from the requirements of a TE to what the kind of hardware that actually makes the TE is, so today we have more or less only one technology, and if we are talking about Android, we have the only technology, and that's the ARM Trust Zone. So I will here explain what the ARM Trust Zone on a very high level is, but there are kind of interesting new technologies coming, for example, from Intel, a technology called SGX that actually may even change the architecture of how the TE will look in the future. So this is by definition not the only architecture, the only hardware we have, but for now in practice on deployed devices, ARM Trust Zone is the kind of the TE environment that does exist. And for those of you who know something about operating systems, a processor typically operates in two different modes. You have a privileged mode where the kernel is running, where interrupts are caught, and then you have the user space where the programs run. And then the kind of the scheduling in the system goes such that the core goes back to the privileged mode, puts a new program to run, and jumps into the user mode for the program. And you can consider the trust zone to be a copy of this. So in ARM Trust Zone, you have the user mode and you have the privileged mode on the Android side, and the Android applications run in the user mode. And on the secure side, we have the same. We have another privileged mode and another user mode. And these are firewalled from each other. And all of those modes, like in a normal operating system, you have a register bank. And when you jump between, you interrupt, for example, between these modes, then there is a certain processor support for storing the registers before you jump into the new environment. You have a stack that is dedicated to each of these modes. And that's how you organize going between these modes in a normal computer. And if you look at the hypervisor is like an extra mode beneath the normal privileged mode. And this is one thing also that sets the kind of the TE apart from a hypervisor. Sometimes you hear people claim that we don't really need this secure world because we have the hypervisor mode, and that's by definition more secure than the privileged mode. This is true, but the hypervisor mode doesn't have a user space. And that means that it's kind of difficult for the hypervisor to arrange running many user applications in parallel, kind of isolated from the hypervisor and isolated from the OS. It can be done, but it's more complex. And because of that, the TE, which actually mirrors the normal operating system setup, is easier to arrange when you actually have the full set of processor contexts. Another kind of, this one is something that used to be called monitor mode. This is a picture from ARM version 8 architecture, and this is essentially a mode that is used for power management, is used for jumping from the normal world to the secure world, checking all that every kind of the entry is correct before actually running the operating system here. This is an extra mode that is put in place for communication between the modes and for managing deep kind of things in the processor itself. In addition to this kind of separation of modes, we also need to separate the memory. We need to separate the interrupts. And all of that is engineered into the ARM Trust Zone architecture. So we have kind of separated kind of interrupt handlers. We have DMA is engineered so that some direct memory access is available to the secure side and not available to the normal world, and even vice versa if needed. The memory management unit is kind of fully equipped to handle in terms of caches and also kind of memory management, so that you can separate the memory, what memory is visible to the secure world and what memory is visible to the normal world. In addition to that, you have kind of on the physical level of memory access, you have access control hardware, so you can actually shield off some memories on the kind of bus level, so that is, for example, only available to the secure side. So you have kind of engineered in the virtual memory system, but you have also engineering on the physical level, and using that you can, for example, in principle shield off some peripherals so that they are only visible to the secure side. Of course, that typically then takes them away from the normal side, and mostly that becomes a usability problem, so that's not so often done. If you look at where trusted execution environments are found today, this is a picture from our company, but in practice we are looking at mobile phones, and one could even say that for kind of even fairly kind of normal priced Android phones up to the high end, or every single Android phone today has some kind of TE. There are TEs from the company I represent, there are TEs from Qualcomm, there are TEs from some vendors from China, and we probably are looking at more TEs that to come in the near future. So there are many trusted operating systems competing in this space, and in some of these environments actually we have two TEs in parallel. So for example in Samsung devices where we are running, in many cases we are running with the Qualcomm TE in the same space, so to speak. But we are also seeing TEs in let's say laptops. There are chipsets from AMD who have a TE. There are also kind of set-top boxes, sometimes use TEs for DRM, and tablets, especially when they are kind of somehow enlarged phones, then they also typically include a TE. And we could roughly say that this is kind of sales margins, but we can say that we are producing TEs somewhere in the range of 200-300 million a year, and if you look at the deployed market today, we have something like 500 million TEs in devices today. So it's not like a rare thing. We have quite a lot of TEs, especially in the mobile space, and of course going forward, what TE vendors are looking at is kind of the car infotainment systems, some degree healthcare and GSM, 3G, 4G, 5G networks, but also going into the clouds and the IoT space is kind of something that is talked about. Now I will switch to kind of a little bit defining the architecture, how the TE looks in Android. So for those of you who kind of operate the Android and look at it with ADB shell or something like that, you actually do see the traces of TEs. You see the traces in certain kernel driver entries in the dev directory. You also see in somewhere around data app and subdirectories of that, you sometimes see secure storage for a TE. That's kind of encrypted files that are encrypted by the trust execution environment and then stored in this part of the flash for its own use. So that's how you see it kind of roughly. Then there is kind of access drivers, libraries by which normal world components can access the TE. And today we have one standard that essentially is defining the trusted execution environment in different levels. We have one standard here called the Global Platform Client Standard or the Client TE standard. It defines what primitives are available to call a TE, to operate a TE. It contains how to push a program there, how to communicate with the program, and of course how to do lifecycle management, like open it, close it, maybe actually deactivate it. And we have the so-called Global Platform Internal API that defines when you write the C code, when you write the program itself, it defines the libc interface, so to speak, that you write against, because inside the secure environment there is no GNU libc or any other tools. You have to kind of go with what is given to you, and for that there is the internal API that provides you with some kind of simple memory management, memory copy, things like that, and then you have crypto primitives, because most activities that happen inside the secure environment is different forms of crypto. You can combine some crypto primitives into some meaningful kind of services. Then if you look at what happens on the Android side, so unfortunately the APIs today are C APIs, and that means that when you now write your trusted application that ends up here, you also have to write something that kind of communicates with that, and that's your normal Java application. But today at least you have to do a kind of go into the NDK and the Java native interface, if for nothing else to link the library that you need to talk to this. And some people in this room have also even provided Java interfaces, so there are some, over the years there have been some attempts to define a nice clean Java interface to communicate with the TE. They have not been standardized yet, and we are still kind of looking at that one has to kind of go the hard way to talk to your TE. And then if you have a third-party provisioning, then you need a little bit more. You need some kind of, so you could call it license management, you could call it kind of remote attestation for the TA, but you need typically something to allow you to push your trusted application here. It can be a business reason, it can also be a security reason, like a smart card. Not everybody is allowed to push programs to a smart card, but instead you are given a key by, in that case, the smart card manufacturer to allow you to push your program into the TE. And that typically includes some native services running in the OEM devices that have this system, and more often than not a network service that kind of participates in moving the trusted application the first time to this side. Typically after that you don't need this network part anymore, and you can just call and use your TA as you like. This is an example of a very, very small trusted application, just for people who know C and who are not kind of scared by other things. It's not that difficult. So this is not, unfortunately, not the global platform API, because I couldn't make it fit into one slide, but this is using our company's legacy API, which is kind of to some degree a subset of the global API. So this is a kind of somehow the most minimal trusted application that you can think of. What it does is that it starts running. It's a main program. It kind of is in the secure side, and here one important thing is that it's given an I/O buffer, something that you kind of communicate with, and that you have to check that this buffer is actually on the other side, on the normal side, because somebody may actually try to fool you by sending a pointer that actually points to the secure side, and maybe that could be the secure side kernel, and you may have actually leak some information. So in a way, you check your pointer, and after that you do a forever while loop. You get an event from the normal side when somebody decides to call you. You do something. In this very simple case, you just copy what you got in this buffer into a uint32. You OR it with something, and you push it back. Of course, you could OR it directly in the input, but that, in a way, would mean that you actually operate on the non-secure side of things. So that's why I'm moving it back and forth, and that's how you typically do it. You get an input, you move the input to the secure side, you validate the input, then you do whatever operation you choose to do with the keys you have, and then when you are done, you have an output buffer, you move it back, and that's the operation you do. In our case, as in most other cases, the compilation chain is really what you would expect in a normal device. You have your trusted application. Okay, here the includes are not kind of in this listing, but you would include some standard libraries. You compile it with an SDK and maybe GCC, maybe somebody else's compiler. ARM has a good compiler. You link it into a binary, then you package it, and in this packaging part there may be some encryption and some signing facilities, and then this package is actually what is kind of moved to the trusted execution environment. And now when we look at the global platform standard, we actually today are in a very happy situation that we have two open source projects that actually enables people to test, to actually do trusted applications and test them in either an emulated environment or on certain hardware boards that are supported. So we have the kind of open TE, which is done in Finland. It's a university project that runs kind of so to speak, trusted applications, but in a completely Linux environment. And we have OptTE, which is a project originating from ST Ericsson, nowadays kind of open sourced in the context of the Linaro kind of working group. And that can be run in an emulator in QEMU, but it can also be kind of run on certain boards that they have listing on their web pages. So both of these can actually be used by researchers and even developers to write trusted applications, to test them before actually deploying them. And of course, as a commercial company, we also have our own SDK, but it's not, unfortunately, open sourced. So going a little bit back to the interaction with the trusted application. So the standard today, the global platform standard, as all legacy systems, do communication this way. So we had the trusted application. You remember the buffer we got. The buffer is actually a shared memory that is shared between the trusted application and the caller. And that means that we have in the user space of the normal world, somebody decides on a memory buffer. The whole path here, the kernel, the operating system here, arranges the memory management such that this program and this program can write to the same memory buffer. And that's actually the same physical memory. And that's how the TEs do their communications today. So when this guy here wants to kind of talk to his TA, he writes something in the memory buffer he gave to the system where he opened the TA, then he sends an event to this guy, and this guy then probably looks for a structure in that memory and starts processing that. So that's kind of the basic primitive of the communication between the secure side and the non-secure side. This also causes a little bit of confusion, and this is something that maybe the compiler manufacturers or even the researchers could help with, is that when you write C code, it's not immediately obvious whether your memory is here or here. But in terms of hardware and in terms of protection, it's a world of difference, because this memory here is actually kind of attackable. I mean, if you have a multi-core system, while one core is operating here, 3 other cores may be operating here, and that memory is in principle accessible by a rootkit, for example. And that means that if this trusted application starts doing secure stuff or important things in this memory because it has a pointer to it, that essentially is information leakage. So the programmer of the trusted application must be very, very careful in his memory buffers. Some are actually protected, his stack is typically protected, but some other memory buffers are somewhere else, and you should get input from them, you should put output to them, but you should absolutely not do anything security critical in those buffers. And because we don't have language support for this, that this means that like yesterday was talked about, there are many problems with C programs like buffer overflows. This is yet another problem, and it's actually in most cases a serious problem, because those codes have to deal with keys that are available here, and if those keys are leaked, in some cases that device may actually be kind of brickable, because many of those keys are such that they are kind of really, if they leak once, they can't be recovered anymore. If you go back to this kind of shared memory, this is one problem we have, and I guess every trusted execution environment provider will have with the SE Android and the never allow rules, because the never allow rules actually very sensibly from a kind of operating system perspective says that any untrusted application in the Android space of course should not be able to access kind of kernel entry points or device drivers directly, and especially not, of course, the TE device drivers. And that means that the coming SE Android enforcement will actually put a blockage so that we can't communicate from the client app through the kernel to the TA anymore. And of course now the TE vendors must kind of figure out a way around this, and I mean logically you do what you do in computer science, you make an extra indirection, so it will be an architecture with some kind of indirection in the talk to the TA. But exactly how that's done and whether we can actually use shared memory in the future through this intermediary will be something that we will see in the kind of Android 6 and forward. But clearly the kind of the standard who kind of is based on the fact that you have shared memory is not immediately suitable to the direction where Android is going. It's not to say that Android has done the wrong security decision. It's absolutely right to not allow untrusted applications to go around poking at device drivers, but it causes an extra problem for the TE vendors, especially if you want third-party use. If you have those applications that were put here to run by default, that would not really cause any new problems, because those services would have typically system services here that talk to them directly, like DRM or the key master program or things like that. Now I will kind of finally or finish up with 3 use cases, and the intention of the use cases is to show what you can do with these, and these are all kind of research demos that we have been doing during the last year or so. Some of these are actually with kind of researchers in this room, and they all somehow were chosen to reflect a little bit different properties of the TE and how it can be used. So the first one is something we'll hear one more talk about today, is kind of electronic IDs. And we all know that you can have the smart cards with electronic IDs, and of course in principle it's trivial to say that we just take whatever RSA signature logic we have in the smart card, we put it in the TE and we are done. And in principle that's so. I mean, it's, you can trivially in a TE do a signature algorithm, it has RSA, and we can do the similar kind of RSA signature that we have in the smart card, we can do inside the TE. But there are a few problems that actually are caused by this system. First, a smart card has the benefit that it's enrolled by a smart card manufacturer on behalf of an issuer. And that means that if you have a government who issues smart cards, there is some smart card manufacturer who will actually do those keys in a factory. And the smart card comes with the key to the user, and the key is already embedded in that device. And that means that you can trust the chain. You trust the smart card manufacturer, you trust the postal service maybe, and you trust that this thing cannot be kind of changed on its way. And the key is in the card, and the key will never leave the card. So it's simple. It's a clear, simple kind of trust chain. Now when we have a TE, where we actually have a device with a TE that's more or less like empty from this perspective, and now we want to actually ask the TE to generate a key and to get it certified towards the government, then you start kind of, you are faced with a question that how do we know that that TE is a valid device and not just some Linux virtual machine that happens to pretend to be a TE. So you have to be able to endorse, authenticate the device, and not only authenticate which device it is, you have to also be able to tell that the key that is generated is not only in the device, but is actually inside the TE. So you have to do, this is kind of solvable by the device keys we have in the platform. It's solvable by kind of endorsement protocols, but it has to be done. Another kind of thing that comes is that the enrollment becomes different. It's not like the phone comes in the post from the government. It's, you actually go with the phone to a police station, or maybe even remotely, like this demo here actually is bootstrapping from an existing ID card. Then you don't have to go to the police with your phone, but we can actually do this remotely if you have a starting point. So in a way, the whole process of enrollment becomes completely different than that of smart cards or passports or whatever. And we have to consider that if we want EIDs in the TEs. And then also, what is different from smart card is the communication path. So a smart card, at least in a PC, you have a well-defined PKCS11 interface, and you use that kind of to access the smart card, get the signature. The phones are not well equipped today to have those paths, so we need something else to be able to use the key for the signatures towards the government. Maybe you want to use it for signing your emails, decrypting emails from other citizens, things like that. So all of that, they are kind of things that can be solved, but it's not as simple as just moving the RSA key from a smart card to the TE. You have to solve those problems 1, 2, and 3 in order to get this done. And in this demonstration we did do that to some degree, but it's a prototype. It was done with the kind of Finnish government, and for now it's exactly that, it's a prototype. Another thing that kind of maybe is this year somehow kind of important, and this was demonstrated in Mobile World Congress this year. So it's the kind of the story of tokenization, and how you can use the EMB protocols like Apple Pay or whoever to actually pay for goods. So essentially what you want to do is that you move your credit card into the device. And this can be done also in many ways. So we can either have the kind of a completely software-based thing. You have a server in the back end that when this phone touches the merchant, it will actually give the token directly. And then maybe you don't need any security. You just say that the network and the secure system in the back end has all that's needed. And I think that's many solutions today deploy this kind of idea. So what you want as a requirement, you want no change in the merchant end, but you want to have a temporary PAN number, a temporary credit card number flowing through your phone into the merchant, and then that will result in a payment. If we have a TE, we can actually achieve partially offline operation, and that means that we can produce the CVV, the checksum, that is dynamic and typically on the backside of your static card. Now it has to be kind of changing every time. We can do that locally in the phone. We can also store these temporary credit card numbers in the phone's secure memory so that they are not kind of shown before they are used. And in this kind of architecture, you don't have to be connected when you pay with Apple Pay, which is kind of, I think, the norm today. So we can use the TE to make the overall security better. But on the other hand, this is a good example where the security actually has been shown that something that was thought to be very important, like an EMV transaction that was done only with a smart card earlier. Now we have actually gone to the other extreme, that payments are accepted at a very low security level without any security whatsoever in the platform, and it still works. So it's also kind of an argument in the reverse end when people say that smart cards are the only acceptable level of security. It's really about the process and the service and what is the acceptable level of risk. And history will show us that it's not always, smart card is not always the smallest or the only possible environment where you can run security services. And hopefully that's good for the TE in the future. But most of those papers and references in the kind of talk, or they are all here. And I skipped one use case because I didn't have time, but I have maybe time for one or two questions.
How secure are these systems against hardware, physical hardware attacks like glitching or side channel attacks?
Right. Again, side channel, let's say proper research side channel attacks, they are not very kind of resistant, because you must remember that they are using the same memory management unit, for example, the same interrupt kind of framework. So for sure, those kind of systems will reveal something about the operations inside. In terms of kind of memory bus snooping attacks, typically those chips that are running TrustZone, or in practice always, they have on-chip memory. So you have some SRAM that is better protected than the DDR outside, and you can actually configure that to be secure. So in terms of, let's say, simple, naive memory bus probing attacks, I think we can make a fairly good end result by having a TE. But for sure, the side channel protection and the hardware protection against, let's say, drilling into the chip. I mean, we are talking about ARM cores that are, I mean, they are visible, they are big, and they don't have a kind of physical protection against drilling through the kind of the top or the bottom, which many smart cards do have. So I think we shouldn't claim that these are protecting against real kind of physical attacks. They are limited by the processor core and the chip packaging that the normal processor has.
Could you talk about the separation that's provided between trusted applications? I've heard from a lot of app developers that want to make use of the TE, but I guess my concern is if there's too much functionality put in there, and that could increase the attack surface.
Right. So this is a place where there are big differences between the implementations of TEs today. So some TEs can run only one trusted application at a time. Others can run several, but they have no memory protection. Let's say, so-called our TE does have, it's a microkernel. It has kind of typical kind of process separation between, I mean, they are multi-threaded applications, and they are separated by the process boundaries with kind of the user space MMU protection. So it is, the separation is kind of in terms of processor kind of support as strong as between two applications on the normal world. You have to add to that the kernel itself is very small, so the likelihood of having a big attack vector in the kernel, in the microkernel itself, which is something like tens of kilobytes, is smaller than having a similar attack vector in the Linux kernel. So putting those together, you could claim that the separation is quite good, but I mean, I'm sure a good researcher can attack that boundary. It's kind of no more or no less what you can do on the normal world side if you would have a kind of small kernel and decent security evaluation of your code.
Okay, thank you. We have to move on to the next talk. Let's thank the speaker, and you will be around for questions in the